rigid body dynamics. Last time we were talking about the moment of inertia matrix. You calculate the moment of inertia with respect to some convenient set of coordinates, but then you might need to find, or it's important to find, the principal axes and then to transform into a principal axis frame. But let's back up and do some things like we'll calculate the center of mass for some objects and things like that. That sounds useful. We want to calculate center of mass and moments of inertia. Some examples. There's an approximation you can make when something is very thin. If it has a thin dimension, then you can use the flat plate approximation, which simplifies things, like the thin triangular plate. But first, what are these general formulas? Well, I mean, there's the total mass. For most things that we'll deal with in here, we're talking about objects with constant density. So if you have some, you love the arbitrary shapes, I hope. The potato wasn't quite arbitrary enough. So this is a sweet potato. Pretty arbitrary. And it's on a plate, which will be used as my thin object later. Okay, here's an arbitrary shape. We've got some frame. It doesn't have to be in the body. Here is a small either mass element, or you could say it's the density times the volume, and you want to integrate over those. If I wanted to get the total mass of the body, then I'm basically integrating, let's call this thing, use fancy B for the body. We're integrating over the body, all the mass elements, just the density. So we're either integrating over mass elements, or you could see this, we're integrating over density times the volume element. And usually we'll think of this dv, we'll break it up into three components like dx, dy, dz. So then it would be a triple integral over the body of the density at that point. Maybe I'll write it this way. The location of the mass element dm with respect to some point O, and then dx, dy, dz. Of course, you don't have to use Cartesian components. If you have a body with spherical symmetry, right? If body has spherical symmetry, then you use spherical coordinates, or cylindrical symmetry, you use the appropriate dv. So here's something with cylindrical symmetry. It's a solid, like this is like a cylinder made of steel. I don't know what it's doing on my desk. It's frightening the potato. I have a cone shape. I didn't have cones. I hoped I had ice cream cones. It's a big food theme here, but I didn't. So I used Play-Doh and made this awful looking purple cone. This is getting dangerously close to not a rigid body, but a squishy body. And we don't want to deal with that quite yet. So that would be the total mass. Often you'll just take the density and multiply by volume. If density is constant, or we say uniform throughout the body, then the mass is density times the volume of the body. And if it's some typical shape, then you could just look it up. Here's a meme. I thought it was funny. So, here's some typical shapes and their volumes written in terms of their dimensions, right? This picture speaks volumes. Nice joke there. So often you could just do that. And then to find the center of mass is a bit more involved, right? This picture speaks volumes. Nice joke there. Yeah, see, I can't even hear you laughing. You're not laughing, but not the hardest thing in the world. If we want to find the center of mass, so there is some spot. I don't know where it is. This is arbitrary. Let's put it here. I don't know why it's here, but there it is. And the book seems to use capital R for that. So center of mass, that means the location of the center of mass with respect to a point, whatever you've chosen as your origin. But the book just says RC. Okay, RC. Good enough. How do you find the center of mass? Well, it is 1 over the total mass, and then you would do this triple integral over the body of the location of the mass, all the mass elements, times the density, and then dv, where we know we could always write dv as dx, dy, dz. So that gives you the location of the center of mass, because we want to highlight this. Calculating the moments of inertia is more involved, but can be done. You need to do integrals, although there are things you can compare with. So one big approximation is if you have a thin plate or a planar rigid body. This would be also the thin plate approximation. It's an approximation because anytime you have something thin, so here's a plate, this isn't exactly flat, but it's got 2 dimensions that are pretty big compared to the third one, very tiny. So if we have a negligible or thin dimension, then we can simplify the calculation of things. Bodies with a thin, negligible dimension. If you have that, then you could use the thin plate approximation. Just to make things simpler, I'm going to take the thin dimension to be along the B3 direction. So if I were to sketch a thin object, it's got a center of mass somewhere, and it's got some body fixed directions. So I'm choosing B3 to be along the thin direction. So B3 is normal perpendicular to the body, because the body is in one plane. That is another thing, all in one plane, planar. And this dimension, we'll say, is thin. It's so thin that when we integrate, it'll just sort of drop out. So that's sort of what I'm getting at here. So if we have the moment of inertia matrix about a point, let's just say the center of mass, it could be other points as well. And we're writing this with respect to the body fixed directions. I'm going to say the density is uniform. So I'm going to pull the density out, and then we just have a triple integral of, and I'll just write all of the components. So we have y squared plus z squared, negative x y, negative x z. That's the first row. And then this is again negative x y. This is x squared plus z squared, negative yz, negative xz, negative yz, x squared plus y squared, dx, dy, dz. So x is along the B1 direction, right? Each little component of mass that we're integrating over, this would be, well, this would be y, this would be x, and z is approximately 0 because it's thin. So because z is approximately 0, all of these things that involve z go to 0. Oh, what do you know? It's in here. 0, 0, 0. Oh man, this is great. Everything just sort of drops out. Well, not everything. And so what we're left with is things that are easier to calculate. So this will be just I11, I12. This is also I12, I22. And the others are 0. And if you look at the integral for I11 and I12, you'll see that this is y squared, this is x squared. So, and over here it's x squared plus y squared. So I33 is equal to I11 plus I22. So this is true. All this stuff is true when you have a planar rigid body. We did choose our directions appropriately. Here's my frame. Here's a flat, roughly flat plate. I'll put it this way. So I've chosen my B3 direction to be normal to it, and then I can write things this way. When you do have a planar rigid body, the B3 is already a principal axis. B1 and B2 are not, unless you have that I12 is 0. So if you don't have these off diagonal elements, that means that you need to do something. B1 and B2 are generally not principal axes. So to find that, you will have to calculate eigenvalues. So for example, if I had a right triangle, I could find its center of mass. I don't know, maybe it's somewhere around here. And then if I did my integrals of what IC B is, these B directions, I've got, this is just in the plane, B1 and B2 for a triangular plate, you're going to get a non-zero I12. So you'll get that there's I11, I22, and you'll get I12 that's not equal to 0 in the B frame. There are, however, other directions. And I don't know, depending on the base and the height, I think they'll kind of be pointed this way. They have to be perpendicular to each other. What is this angle? Well, I guess I could write it more suggestively as a capital phi, then maybe it's more obvious. All right, so you could find out what that is. That means there are directions. I don't have a triangular plate. I do have a YAM, but not a triangular plate. If I had a triangular plate, that means there's some directions that I could spin the plate and it could do pure rotation. But it's not just the kind of easy to work with B1, B2 directions. And it also depends on the, what do we call this, B, and then this, the height. if you do have something that's in a principal axis frame, so that this was a triangular plate, what about something else, a flat circular disk, flat disk with mass m, radius r. I don't know what the radius is here, like 5 inches or something. Mass m, radius r. Well, because of the symmetry of a disk, so let me draw a disk sort of seen from a side view. Should be straightforward to find out where the center of mass is. It's in the geometric center of the disk. If we're talking about uniform density, nothing tricky. We're not tricky here. Has a mass m, and if we follow this procedure of making B3 be normal to the plane of our planar body, and then B1 and B2, seems like any B1 and B2 we choose, but due to symmetry, are going to be principal axes. So I guess that's something I didn't mention. If you have a body with a certain symmetry, then there's no distinct principal axes. So like a sphere, any direction is a principal axis. If you had the ability, you could spin the Earth about any direction, and that would be pure rotation. Okay, so if this has mass m, radius r, and you could do the integrals, but you could also easily look it up for simple shapes. I11 equals I22, and this is 1/4 mr squared. It's the same in both, but due to the rotational symmetry. So I33 is the sum of those two, but they're the same. So I get 1/2 mr squared. Now, how do I interpret this? I interpret this as it's twice as hard to get a disk rotating about the axis of symmetry as compared with any axis that's in the plane of the body. And you can even feel this if you have a heavy enough plate. And this plate isn't quite heavy. Pick up a manhole from somewhere in Blacksburg and don't tell them I told you to, but try it. And then if you try to get it rotating about, this is rotating about that B3 axis, and you can feel that's harder than rotating about any other axis that goes through the body. Interesting. You could look up things like the center of mass and the moment of inertia for some standard bodies. This is moments of inertia of selected bodies. Flat rectangular plate, and this uses the symbol G for the center of mass, but I think you can figure it out, right? This is saying for the flat rectangular plate, here are the moments of inertia, and right, this is already using that approximation, because notice the I33 component is equal to I11 plus I22. Plus, the way that they've chosen the directions, B1 along kind of the X direction or the width, and B2 along the height are already principal axis directions. For a flat circular plate, that's just what I showed already, and any directions because of the symmetry, B1 and B2 will also be principal axes. This is showing the flat triangular plates. This would be a good thing to compare with. Oh, don't take screenshots now. You don't have to. I'm going to provide this. This is for something it's got this extra gamma thing. This is just showing like an even more arbitrary triangular plate. It doesn't have to be a right triangle. Here's a thin rod. Thin rods are weird. There's a 0. That means there's some direction where it's easy to rotate about. I guess they're saying like if you have your pencil, you could rotate it easily about that. And it's harder to rotate about any other direction. Of course, it's not 0. We're just assuming a cylinder that has vanishingly small radius compared to the length. And then this thing that it calls solid rectangular parallelepiped, most of us would call that like a solid box or block, but they're trying to be very, precise here. Solid circular cylinder, would it be this bad boy right here? Thin circular shell will be this double shot of Starbucks that has me amped up, although with no end caps. Solid sphere, a solid cone. Oh, check it out. Cone. So the center of mass, where is that center of mass? Well, maybe we'll calculate it. It says it's something over 4, whatever. And then you have a thin conical shell with no cap. I think that means an ice cream cone. Solid hemisphere, solid ellipsoid. Wow, this is just a treasure trove. Well, I like that it uses our notation, more or less. You could find tables online. Where's the center of mass? Some bodies have obvious symmetry. So these are center of mass for common 3D objects. Actually, these aren't common. These are like platonic objects that don't exist. Most things are arbitrary. But for the simple shapes, let's say there's a sphere and you're like, huh, where's the center of mass for a sphere? Well, it's in the geometric center. Okay, great. So nothing to really calculate. Here's a cylinder, solid. This would hurt if it fell on your foot. Where's its center of mass? Well, it's probably in the middle, and I could, the geometric center again. Those shapes are just stunning. What about a cone? I don't know how to draw a cone. Can I? Yeah. Okay. There's the cone. It's not obvious to me where the center of mass is for a cone, but you could calculate it. Yeah, you could calculate it. So the center of mass is by symmetry, it needs to be somewhere along this axis of symmetry. So I don't know, it's somewhere on there. So really, we're just having to calculate like what's that height from the bottom, the middle of the bottom of the cone. All right, here's a cone, here's a middle of the bottom, and then it's somewhere, probably not halfway. So I'm guessing it's somewhere in the lower half. And you might say, well, can I experimentally find it? I could try to, yeah, good luck. For flat plates though, you can, like the triangular plate, make yourself a triangular plate, and then you could actually just balance, find out where the center of mass is. Like this is going right through the geometric center, or the triangular plate, it's somewhere else. So let's set this up as an integral. Let's set it up. Oh boy, I love integrals. I don't, but it's a necessary part of life. Eventually, you let machines do it, but you need to understand what's going on. So if I choose as my just a convenient origin for doing the calculation, the bottom middle of the cone, so maybe I'll call that O, and it doesn't really matter what the other two directions are, but I should make this at least the one axis be along the symmetry axis. And I'll say that this cone has a height h and a radius of r. Base has radius r. Then what? We go to the formula. The formula says you do 1 over m, and we'll worry about m later. You could look up what m is, right? M, so m for any object is going to be rho, the volume, and we could look up what the volume of a cone is. I think the volume of a cone is pi thirds h r squared. So that'll come into play at some point, but not yet. Let's just leave it as m. Then we're doing our triple integral over, this is our body, density times, if I were to just sort of show some arbitrary volume element, or dm, which is rho dv, and we call this RDMO. Then we're doing R, and I could almost write it as just dV, location of that volume element, O, times volume element, dV. So this is dV, and if we use cylindrical coordinates, in cylindrical coordinates, that's the easiest to do it. So that would be R theta Z. What is dV? dV is R d R d theta dz, and the location of this vector are, maybe I'll make this a little bit clearer, location of dv with respect to O. I don't know if that made it any better. dv with respect to O. We're just writing polar coordinates for this thing. So it's going to be, sure, I'll use that color, R cosine theta. And if you're like fretting about where's theta, okay, theta would be like angle, the angle with respect to the B1 direction, and the B1 plus R sine theta B2, right? It just looks like polar coordinates in B1 and B2, and then Z in the B3 direction. We can do that. Okay, so now we set this all up. We've got our triple, we pull out the density because density is going to be constant. So, and we could even substitute in, this is rho over the volume. Oh, what do you know? The rows cancel. And then we have a triple integral of r dv o. What is dv? dv is r dr d theta dz. And right now I'm saying this is an integral over the body, but I'm going to have to put in limits of integration. Ooh. Triple integrals are not fun. Thanks. Didn't know that. But they can be done. So there'll be an integral over z, an integral over theta, an integral over r. And I might even just switch the order so that it matches what I'm going to do. I'm going to do, right, you go from kind of the outside, the inside out. So 0 to h dz, giant parentheses of, now we're integrating over radius 0 to, and I want to get a formula for how the radius changes as a function of z. Remember, z is measured from the bottom, and this would turn out to be, and this be left as an exercise for you to do this, 1 minus r times parentheses 1 minus z over h. We're integrating over radial direction. Another parentheses, 0 to 2 pi. So now this is the integral over theta of our vector. And we've conveniently written our vector right there. So r cosine theta in the b1 direction plus r sine theta b2 direction plus z b3. And now I just need to close up these parentheses. 1, 2. I feel like there should be a third one somewhere. 1, 2, 3. Maybe I'll make the big outer one be square. Now I wrote the integral this way. You might be thinking, okay, you wrote over here, it looks like vectors. Yes, so technically you could separate out, there's an integral for the B1 component, an integral for the B2, and an integral for the B3. So this is actually 3 integrals, one for each of the directions. But since we know we're on the symmetry axis, the integral for B1 and B2 is going to be 0. So you could maybe see that. Due to symmetry, the components in B1 and B2 are 0. So if you did that integral, they'll go away, right? What's the integral of cosine theta from 0 to 2 pi? Well, you have just as much area above 0 as below 0. So it goes away. 0, okay. What about sine theta? Same thing. Just as much area above as below. What are you talking about above and below? Sine. All right, we've got, this is positive, this is negative. So this integral is 0. Okay, so that means we're only left with a B3 component. So we could write what's left. That would be, right, if you integrate, this doesn't have any dependence on theta. So you integrate 0 to 2 pi of d theta, and you just pick up a 2 pi. So this will be 1 over the volume, 0 to h, square bracket, 0, capital R, 1 minus z over h, 2 pi rz in the B3 direction, dr, dz. Okay. Okay, we'll do that interior integral first, the one in the square brackets. And that's just an integral over r. So that's not too bad. And I've got r here. So this will give us, I'll bring out the 2 pi. And then in the brackets, this is going to be 1/2 r squared, evaluated from that to 0. And then there'll be z dz. Okay, if I evaluate that, let me just bring out this 2. The 2's cancel. Boom, boom. And I have capital R squared, 1 minus z over h squared z dz. Okay, so now I have an interesting integral over z because there's this something going on there. Okay, you do that. At this point, I'm hoping you could reliably do one-dimensional integrals. Like, where? Oh, you dropped the B3. Okay, I did. Here it is, B3, B3. It turns out you get pi over 12, h squared, r squared. Yeah, this has dimensions of length to the fourth. V has dimensions of length to the third. So if we then substitute in what we have for V, and it's been so long since we looked at it, pi over 3 h r squared in the upper right up there. Okay, got it. 1 over pi over 3 h r squared h squared. So many pi's and things. Wow, the r's cancel out. Got some pi's canceling out. We're left with h over 4. And I am forgetting this B3. This is a vector. Remember what this was? RC. So RC is h over 4 B3, meaning if I have a cone, it's 1/4 of the way up. So start from here, go up 1/4 of the way on that axis of symmetry, and that is C. So what I calculated was this vector RC from the bottom. That's it. So center of mass of cone is 1/4 of the way from the bottom on the symmetry axis. So yes, you do have to do integrals. I'm not going to tell you integrals are your friends. We should probably talk about calculating the moment of inertia. This was all just to find where the center of mass is for something. So how about calculating a moment of inertia? We could do that using integrals. Just to make life easier, how about we start with planar bodies? So here is it's going to be a perfect square, no matter what you say. It's a perfect square. So this is a square flat plate with sides. Let's just call them L. Nah, let's call them 2L. That'll make my life easier. 2L. There you go. That's kind of tricky. Why would you just call it L? Helps with doing the integral. So I know this is a square flat plate, uniform density. The center of mass will be at the geometric center. And then convenient directions, which are, I'm guessing, also principal axis directions. Be these B1 and B2. Cartesian components will do fine for calculating where things are. So here's, I'll just write it as R because this is a mass element, dm. I'll calculate I33. So if this component is X, this component is Y. I33 would equal, I've got a uniform density. And here, if you have the flat plate, instead of a volume element, you're actually integrating over little area elements. So this is rho dA. dA is going to be dx dy. So pull out the density here. And just from the formulas, this would be double integral over, it's a planar body, x squared plus y squared dx dy. And if I am careful about what the limits of integration are, this is where it's convenient to write the sides as length 2L because I'm integrating from negative L to L in both directions, x squared plus y squared. And you can do that. Here's what you'll get. You'll get rho 8/3 L to the 4th. And now we need to know what the density is. Well, for this thing, since it's a planar body, mass is and I guess this is another thing. You usually want to express the moments of inertia in terms of the mass and dimensions of the body. L is already an important dimension of the body. You could leave it like that. This is correct, but typically you want to express in terms of the total mass and dimensions of the body. So M here would be density times, because it's a flat thing, basically area. So there was, I guess, a little trick here where I'm saying density, which you might think is mass per unit volume, but for these flat things, you could treat it as mass per unit area. What's the area of this square? It's 2L on each side, so 2L squared, so 4L squared. And so then using that, we could find out what's rho in terms of the total mass, plug it in there. So I33 ends up being 2/3. There's a 2, and then the third is still there, ML squared. And that, I'm guessing, agrees with what we had in our little lookup table. Flat rectangular plate. So just based on how they wrote it, what we have is a special case of a flat rectangular plate where W and H are both equal to 2L. And if we put that in there, what would we get? We'll get, yeah, same thing. So you could, also calculate for a circle or a ring or whatever. There's this useful thing that I don't think I've mentioned, the parallel axis theorem in 2D, you may have seen, but there's a parallel axis theorem in 3D, and it is very handy. The book does mention it, but it does not say very much. I think it is equation 4.22. And how is this useful? It's useful if you have or can calculate the moment of inertia about the point O in the body fixed frame, or you have or can calculate the moment of inertia about the center of mass. There's a relationship between the two. So whichever one is easy to calculate using the integrals or whatever, then you could transform it to the other using the parallel axis theorem. So you can get the other. So again, arbitrary shape. Maybe you choose some convenient point O, but there's also the center of mass and the location of one with respect to the other would be RC, kind of what we've been using. And that means location of C with respect to O. The direction matters because you don't want to mess this up. So the 3D parallel axis theorem or formula or whatever you want to call it just relates these two in the same frame. IOB equals ICB plus the total mass. And then if you remember these tilde matrices, you're like, no, I don't. Okay, that's all right. It could be written this way, which is probably easier. You just write the magnitude of that vector squared times the 3x3 identity minus that vector written in the body fixed frame, a column vector, times that in the body fixed frame as a row vector. So this is probably the easier one to implement. And it goes both ways in terms of if you have the moment of inertia about C, then you could get it about O, or if it's easier to get it about O, then you could calculate it about C. So as a completely arbitrary example that just fell from the sky, if we had a flat triangular plate dominating the screen, then for this, it's easiest to use the corner to calculate IO, right? That corner with respect to the given body fixed frame. Then use the 3D parallel axis theorem, ICB, given RC. So you'd also need to calculate RC. So for that problem, you're going to need to do integrals to find the location of the center of mass. You'll also need to do integrals to get this, but then you could use the parallel axis theorem to get moment of inertia about the center of mass. That's what I want you to do. And then once you have this, you're asked for other things like, what are the principal axes? And we've talked a little bit about that. They're definitely not B1 and B2. They're not those convenient things. They're going to be off by something. So that's the parallel axis formula. I was going to say something about when you have a compound shape. If you have a complicated shape given you by like a CAD model, which is going to be typically what you get, then like for weird things, I don't even know what to call those complicated shapes. Things that aren't triangles and squares and rectangles. Complicated shapes can be approximated with a bunch of smaller, simpler shapes. And then you would like use the parallel axis theorem. So if you have, what's a nice example? If I had a shape that was, say, like an L shape made of metal, I could treat this as, I'm not going to be able to look up L shape. I would treat it as a bar going that way. So this is the body. I could treat it as one body plus another body. So you treat as composite bodies, treat as that is the technical term, I think, meaning it is a body that is made up of a union of other things. I mean, we could put plus, but maybe hopefully you get the idea. Like that means it's the joining of them. So that would mean that the integral, whatever integral we do over the body is the total body will be the integral of body one plus the integral of body two. You just need to be careful about treating them with a common origin. And this works for an arbitrary number. Here, I treated this L-shaped bar as the sum of only two, but this works with multiple bodies as well. So if I have an arbitrary shape, please show an arbitrary shape. Here's an arbitrary shape. Well, I could treat this as, I'd say, well, there's a big chunk of it that looks kind of like a rectangle. And then there's smaller pieces that maybe look like bits of triangles and whatnot. And I could just sum all of those up. Like this isn't the best, but hopefully you get the idea. So I've taken this shape, decomposed it into some number of bodies, and they're simple shapes that you could even have a lookup table for them. So this is probably what behind the scenes CAD software would be doing if you were to ask for what is the moment of inertia. So decompose into simpler shapes. So this is what CAD software does. I guess you could think of it as a finite element approach. But when I think of finite elements, I think of sometimes, everything's like a tiny element. But here you might think, well, there's a big chunk of this that's just a rectangle. Suppose you have an arbitrary shape. The shape of Mexico. It's a pretty arbitrary shape. And here it is approximated by a bunch of rectangles of various sizes. I don't even know how many, maybe 10,000 rectangles. Wow. Okay. That's neat. Here's a rabbit approximated by triangles. If you've done anything with computer science or computer graphics, they love this rabbit. They just love the rabbit. And they like doing adaptive meshes of the rabbit and stuff. So if you wanted to get what's the moment of inertia of a solid rabbit, it kind of makes sense. With Easter, chocolate rabbits get eaten. If you want to spin them. No, nobody does that. Nobody does that. On the subject of rabbits and squishy things, here is a squishy rabbit falling and bouncing. So this is not operating as a rigid body, it's squishy. This will go on and on. Let's drop it from a different position. Oh, boing, 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 boing. This was from somebody's thesis. Not here, I don't know. There's this weird thing at the end of just like a bobble-headed cat. You're like, yeah, you knew squishy bodies would show up again. As another example of an object, right? You could have a flat thing, flat body, and then you fold it. I used to assign this as a homework problem, and you will be glad that I did not this time. Well, I guess I still can. Yeah, I guess I still can. Here's a flat triangle. Right, and you're like, okay, what about it? Suppose at those perforations, I fold this thing up to a 90-degree configuration so that it looks horrendous. Look at that. So I'm like, okay, take the triangle, fold it into this, and then find the center of mass in the moment of inertia. That's something that can be reasonably done. What do I have? I have a model of this, so it could be experimentally verified. There it is. It was on my desk. It was just sheet metal. This is before potatoes and yams dominated the desk. There was sheet metal. And these tips were very sharp and might hurt me, so I had to cover them with tape. Yeah, there's the object. And the center of mass, oh man, this is rough. But what you could do is you take this shape. You could decompose this into some basic shapes. So if I were to decompose it, I'd say, well, I know about triangles and I know about rectangles. So I'll decompose this thing into 5 shapes. 1, 2, 3, 4, 5. And where are those correspondingly in 3-dimensional space? This is 1, this is 2, this is 3, this is 4, this is 5. Well, you know everything that there is to know about triangles and rectangles. So you could actually calculate the center of mass of each, and then you could find out the overall center of mass, right? The center of mass of this, oh, it's easy. Center of mass for right triangles. Spoiler alert, it's 1/3 of the way. If this is the corner, it's 1/3 of the way in both directions. So it's like there. And so you've got all these centers of mass and their masses. So then you could calculate where's the overall center of mass. And the overall center of mass, it can be found. It's not the end of the world. It's not a picnic though either. It's some distance, along here and then along here and then up. And so there's some kind of overall center of mass. And in that projection onto that direction, I could experimentally verify that. I did this. Someone else gave me another version of it with a harder metal, and then they identified where the center of mass is and put a nail in it going through that center of mass, right? Because things balance through their center of mass. So yeah, you could take shapes and then you get not only the total center of mass for the body, but calculate the moment of inertia. Oh my goodness. And then find out where are the principal axes. If I took this thing into the space station and spun it, what's it going to do? I think I've said everything that I want to say. Next time, we will get into legitimate rigid body dynamics. We've been still setting up getting what we need to actually calculate rigid body dynamics for objects. But next time, we'll look at Euler's equation and okay, what are the dynamics? That's it.